We already have our stiffness, then we'll proceed now with our next step. Our next step involves the calculation or the determination rather of our stiffness matrix and as well our mass matrix. For the stiffness matrix, that is just equal to for a three-story building, we have K1 plus K2 and then negative K2, negative K2, and then the K2 plus K3, 0, and then we have 0 here, negative K2, negative K2, K3 rather, negative K3, and a positive K3. So just add that up. We have the K1 plus K2, so we have 10,903,666.05 Newton per meter plus the 21,296,222.75 Newton per meter. Then the negative T2, negative 21,296,222.75 and 0. And the rest is like this. So we just follow the pattern that we have for our stiffness matrix now, like this, such as this one. And then, so eventually we'll have our stiffness matrix as equal to as shown here. So we just added no, the stiffness that was as, or as shown there. We have the K1 plus K2 and then the K2 plus K3. And eventually we will get this stiffness matrix. That is for the stiffness matrix. Next is we need to have our mass matrix. Our mass matrix, so the symbol for the mass matrix is this one. Let's say that is the symbol of the mass matrix. The mass matrix is just equal to M1. So the diagonal for the mass matrix will be our masses per story. And then the rest is just equal to 0. We have our mass for the first floor as 5,000. And the rest is 0. Then the mass for the second floor, that is 2,500 kilograms. And then the mass of the third floor is 1,250 kilograms. Now, when we're dealing with the stiffness matrix and the mass matrix, since later on we'll have operation that will involve these two matrices, so will try to simplify the equation. We try to factor out what we can factor out. So for the mass matrix, as for me, if you look closely with the stiffness matrix, we have uh, the digits up to the million. And with our mass matrix, we have up to 1,000. So we can factor out the mass matrix in order for us to have no large decimal displacement or digits in our calculation. And then for our mass matrix, we can use to factor out 5,000, one or the 2,500 or the 1,250. It's up to you. But it would be best if we factor out 5,000 from the mass matrix. If we factor out 5,000, we'll have 1, 0, 0. So that is 5,000 divided by 5,000, that is 1. And then 2,500 divided by 5,000, that is 0.5. And then the 1,250 divided by 5,000, that is 0.25. So this is our mass matrix. Now the next step no, in our calculation is we need to subtract from the stiffness matrix the mass matrix, which is multiplied by the omega squared. Again, if you remember, our mass matrix is just as this, and we have the minus omega squared times the mass matrix. So by the way, no, if the mass matrix, we have the 500 and the matrix. So we have the times 500 and the mass matrix as shown here. If you notice, there is a 5,000 that was being factored out from our mass matrix. Now, in this problem or in this given operation, we can divide the whole equation with 5,000. So we can divide, let's say multiply the whole equation with 1 over 5,000. We can use this one. Now, if we divide 5,000 to the whole equation, the new stiffness matrix will become, so we just actually you don't need to spread out to this one. You just divide 5,000 to every single values that is present there. So we divide to 32,199,888.8 with 5,000, the 21 million, the 47 million, and the 25 million, etc. with 5,000, and eventually we'll have our stiffness matrix equal to this one. This is our new stiffness matrix. And then on the other side, we have the 5,000 divided by 5,000. That is just equal to 1. So minus omega squared times the mass matrix, the 1, 0, 0, and then the 0, 0.5, and 0, and the 0, 0, and the 0.25. Now, later on in our calculation for the mode shapes of the this given or this specific multiple degree of freedom system, the omega squared might be bothersome to some people. So for that, now here we'll be dealing with the cubic equation. So the omega squared. So for a three-story, we'll have a cubic equation that will be formed in our calculation later on, and the omega squared will be raised to the sixth power. And for that, to since it is bothersome for other student, let we can let the omega squared as our b, or let b is equal to omega squared. So in such a way that later on we'll not be dealing with the omega to the sixth, omega to the fourth, and omega squared, but instead we'll be dealing with just the b. So let me erase the omega squared there and then replace it with b. So that is equal to the stiffness matrix. So let me just write this value here as this with this symbol, since there are too many quantities and digits to be written there, minus. So what happens next is, since we have a multiplication here, we just distribute the b on the matrix. So we multiply this to everything, but since most of the digits here number is 0, then we just multiply it to the masses given. So minus, then our new mass matrix will become b, and then 0, 0, 0, 0.5 b, 0, and then 0, 0, 0.25 b. Okay. So after that one, we have already simplified the mass matrix side. Now we'll need to do the operation. So we have a subtraction here. So what that means, we need to the stiffness matrix minus the mass matrix. So to do that one, this specific row and column will be subtracted here, and then this one to the second column here, and the first row, second column, and then this one to the other side. And then for the middle row, also for the middle row for the mass matrix, so on and so forth. I mean here, we'll have our matrix. Now this is a much more simplified version of the stiffness matrix minus omega squared matrix. So we have the 6,439.978 6,439.978 minus what is present in the mass matrix, that is B. So minus B. And then we have the negative 4,259.245 minus what is present in the mass matrix part, that is 0. So we need not write that in our simplified matrix. And then 0 to 0 minus 0, that is just a 0. And then we have 4,259.245. Then we have the 9,428.39, 9,428.39 minus this one, 0.5b. And then we have negative 5,169.146. And then on the other side, we have 0 here and then negative 5,169.146 and a positive 5,169.146. So this part here is our stiffness matrix minus omega squared times the mass matrix. So whenever we talk about this, it means this matrix. So this is the simplified form already of the subtraction of the mass matrix and the stiffness matrix with the application of this B, which is just equal to the omega squared, which is our natural frequency of the system. So take note for that one because we'll be using this when we'll be dealing when we're calculating for the mode shape factors.